Good afternoon again. You're welcome to What Do Geophysicists Do? And this is Next Gen, if you're just tuning in for the first time. And we're a stream under AFB Scotland. Just a little bit about AFB Scotland. AFB Scotland is a non-profit organization which was founded in 2011 in Aberdeen. And the aim is really to promote like higher education in engineering and even other, sectors as well in Scotland and even everywhere really, because there's some people watching from Australia, some people watching from England, so that's really our aim. And in AFB Scotland, there are 4 streams. There's the Next Gen stream, which is this platform that you're tuning in on. And this stream actually promotes increased STEM participation of school children between the ages of 6 up until 19 when you go into uni, or even 18. Then the next stream is transition, which solely focuses on university students who want to push into the professional world, and it helps them into getting into the industry, coaching them and training them to get into the industry that they desire. We also have the Real Project, which is a platform where different professionals from different backgrounds actually come and share knowledge between each other. And we have the Leadership stream as well, which promotes actually, it promotes professionals in the industry and also trains them and motivates them to attaining that mentoring, attaining that managerial position. We also have the mentoring program as well, which support young people in terms of back-to-back mentoring. If you want to mentor people, if you want to become a mentee, we also promote that. So these are the different streams of AFB Scotland. And this is Next Gen. So you're all welcome here. This happens every other Saturday of the month. So having said that, we'll be having another session in 2 weeks. And today we're going to be listening to Ipsita, who will be talking about what geophysicists do. And I'm just going to give you a little introduction about her because she's quite loaded. So I'm just going to try and summarize it into a very short, introduction. So Ipsita is a self-employed geoscientist living in Aberdeen, Scotland, with her husband and 2 children. She has 20 plus of experience working in the upstream oil and gas industry, plus with independent oil and gas companies and also in the consulting sector. She has lived and worked in UK and India. She also studies data from multiple diverse geological basins such as North Sea, North Irish Sea, Gulf of Suez, West Africa, East Timor, Australia, Colombia. So it's quite a lot. So she's loaded. So make sure you're listening today because you're surely going to learn a lot from her. She has also, she's also very passionate about driving STEM initiatives among schoolgoers, particularly students in the area of earth sciences that have suffered from gender imparity and lack of diversity. She also feels it's important to engage with young-minded people and also promote honesty and candor to win their trust. So this is Ipsita, and she's going to be talking about what do geophysicists do. So if you want to hear a lot about what she has in her brain, as you can hear, she's quite intelligent. Please welcome Ipsita. Welcome, Ipsita.
Thank you so much. That's loads of words. Hopefully I can keep up to it. As you said, I have done these kind of presentations in schools before, and especially trying to promote science subjects, physics, or in general a specialist geophysics among girl students, because when I was a student doing my geophysics, I had very few other female students studying with me, and I would always it's a thing which is very close to my heart. I would want more and more women join into the industry. So without, I think we have got most people already joined in. And so I think I would start my talk today. It's titled, What Do Geophysicists Do? Because that is a question which I have had from a lot of people, you know, even back home in India, if I go and say somebody and they ask me, what do I do? So that takes me to the next slide about who am I and what do I do? The expression that I have always seen from people is, what? A geophysics? What do you do? So coming back to it, I'm not really one who moves around with a hammer breaking rocks everywhere, but there is something else that we specialize in terms of degree that you need to do, whether before you can start working as a geophysicist. This is mainly for, you know, hopefully we have a few students or teenagers who would want to do later. So I had my graduation was done in physics, and then I specialized on my post-graduation or master's from Indian School of Mines in applied geophysics. And there's, can you see my mouse? Can you see my cursor?
Yes, we can.
Okay. So yeah. This is a little picture of my alma mater there. And when I say a geophysicist, well, my experience is has been mostly with the oil and gas industry. But as a student, I have done my internship with mining company. So I had a little bit of exposure to what mining geophysicists do. And of course, my dissertation work was on seismology. So there are other things that a lot of other geophysicists do, and a lot of other friends from our university who work in other industries, and hopefully today we can talk a little bit about all of them. So the first of all, and if you're talking about the various industries that geophysicists work in, of course, they work in oil and gas exploration like me and many others who look for oil and gas all over the world, both offshore and onshore. But you also have seismologists who would be looking in more details about, you know, if you have any earthquake, prediction of earthquakes, which are the places which are prone to earthquakes, and all sorts of study that, you know, seismologists would be involved in. And you also have mining geophysicists who would be working in kind of the mining industry in, you know, be it a gold mining or copper mining. These are all, you know, minerals that we really look forward to, you know, exploration goes around all over the world. And that's what mining geophysicists would do. And of course, I don't know why it's a bit laggy, sorry. And then we have got atmospheric geophysicists, and they specialize in the upper atmosphere. So they're looking to investigate the Earth's magnetic field and electric fields, and then compare that with the outer atmosphere, with what we have with the other planets and everything. So they study atmospheric dynamics, the climate change, and other meteorological phenomena that's happening around. So they're all involved into those kinds of meteorological investigation. And of course, we then have environment. Sorry, the people still joining in, and hopefully, you know, they can catch up. So then we have environmental geophysicists, and they focus on the physical properties of the shallow subsurface, you know, just beneath the earth, the first few kilometers and meters. And what they do is they would map and identify if there is any potential movement of surface water or groundwater, or to identify if there are many contaminants in the soil. So those kind of, I mean, especially possibly living in UK, we do not see much of that happening, but there are all parts of the world where groundwater exploration is a major issue, and there's quite a few of our friends and colleagues are actually working in the groundwater exploration industry. And then we have also marine geophysicists who would be involved in large scale kind of marine exploration. What
so
comes
that
under
means,
is like if
so that
there
means,
are any shipwrecks.
oh, so that means keeping the water from being polluted.
If you remember, the last I can remember very well was the Malaysian Airlines that went down. And of course, you know, there was a massive hunt to find that particular airplane crash, you know, the airplane as such, under the water off coast of Australia. So the people working on it were again geophysicists, and those we would possibly call them as part of the group of the marine geophysicists. So, but this is only, you know, as I mentioned, this is not a completely exhaustive industries that I've mentioned, but there are other geophysicists working in other fields as well. But these are primarily what I would say I know of, that where geophysics is definitely used as a tool, and it's, you know, a prime focus. But now I think we will move a little bit on the actual oil and gas exploration, because that is what I've done for the major part of my career. About 18 years is what, you know, I've done for exploration oil and gas. And if we talk about that, very briefly, I would say, what is a cycle? I mean, how do you go about doing an oil and gas exploration? First of all, of course, you get an acreage, be it offshore or onshore, and you do mapping and reconnaissance survey. So you do what you would say a very basic mapping to see if there is any potential for oil and gas there. And of course, once you have done a mapping, you go into the next bit, which is a prospect generation, wherein you are kind of, I would say, you have looked into the map and you've kind of pinpointed and said, oh, possibly this is where you could find your oil and gas. So you have generated what we call in our oil and gas industry a prospect. Now, once you have generated that prospect, of course, you have to actually prove that you have oil and gas there. And for that, we come to the next stage of a prospect confirmation and a reservoir delineation. And how we do it is, of course, we drill a well again, and to find out if you have the oil and gas that you had predicted. If you have, then you sit and analyze as to how much you have, whether it can be economically developed. And if you think that it can be done, that's when you go into the next stage for the field development. And of course, in order to develop a field or to actually get the oil or the gas out from under the surface into through pipelines to bring it into for your use into the refineries or, you know, onshore, is what you would say. Of course, you need your facilities to be done, your pipelines need to be stored. And once all that is done, a primary production is started, and we start producing from the oil and gas fields. And towards the end of the life, when you have almost produced everything possibly, you would go towards what we call enhanced recovery, wherein you try other methods to get in whatever oil and gas is left behind still. And of course, this is a cycle, because you go through it. Once you've got the oil, you acquire more acreage and you divest into more other acreage to find out oil. And it's a recurring process that goes on. But when we're talking about the first stage where we said a prospect generator, what do we really look into? And this is what we will go into a little detail a little later, as I said, when we use seismic. And this is just a cartoon showing a few seismic cross sections as to where you could actually, how do you think when you see something on your seismic and you can say, well, this is a place where you possibly could find the oil or gas.
Real quick, because you know, the oil is used as a fossil fuel.
Yes, sorry, I couldn't hear you. What's your question? Or can we keep the question for the end? I think we should have started with that, if that is okay. If you can park your question and we'll come to it.
If you just type your questions in the chat, we'll pick it up at the end. You can go on.
We've kept about 20 or 30 minutes for the end to discuss. I think it might be easier that way.
Okay.
Right. Thank you. Okay. So when we're talking about structures, what kind of things would you look for a seismic? The first things that you would look. So this is a very basic cartoon, but it shows, the first one shows an anticlinal structure. And why we look at in such an anticlinal structure? Because, you know, if you would already know that oil or gas is lighter than water. So what happens is when it flows up, it goes above the oil, above the water. The oil or gas would go above the water, but it will flow away. And in order to stop it from going anywhere, we need structures or entrapments. And so if it is an anticline kind of a structure, you would possibly get at the topmost bit would be your oil or gas that would get trapped in there. But it could be other kind of structures, and these anticlines could form because of diaparism, which is salt. And I'll show you a few pictures, nice pictures of what salt, you know, how it can change structures and what it does later. Then you could have these faulted blocks, and what it means is basically if you think about a rock and it is broken and it's slided down and it's got faulted, so what happens is with the oil or gas coming in and it gets juxtaposed against some other rock where it cannot flow into, and so it gets trapped there. So you might be finding it. Similarly, it could be a syncline, which is an opposite of an anticline, but a syncline with a fault where it, again, you could get it stored. So these are, you know, very, very basic structures that we would start whenever we start mapping, and on a basic reconnaissance level, you would look at your seismic and see if you have anything of that sort, wherein you could possibly get any of your oil and gas. So we have covered a little bit of this, but we'll just go into a little more detail about when we say we have some oil or gas or the petroleum system as such, what are the basic things that we are looking at? First, of course, we are looking at the source, because it needs to be cooked. Anything that's to be there, it needs to be cooked in a kitchen. It's not in our kitchen, but of course it's deep down under the surface where it can be cooked at a certain degree of temperature and pressure, and at a certain point in time, all this oil or gas has got generated. And we need to find out whether that kitchen is somewhere near where we are looking for it. So is there a source available is, of course, the first question we need to answer. And just because there is a source, there is no chance that you can get the oil. To get the oil, it has to be trapped in that place as well. And this is where we were talking about the structures. So say there is an entrapment available. There is a similar kind of anticlinal structure that we were talking about. So what would happen is the oil or the gas would flow above the water. And then if it cannot go above anywhere, then it gets stuck there. It gets trapped. So that's what we call is an entrapment. So do we have a structure? Do we have a stratigraphy? Or can we have a combination of both? And of course, for the oil to go into there, we need a reservoir. And when we're talking about reservoir, it can be of different, quality. And there was one presentation I remember giving to a school regarding, what kind of reservoirs we get and how do we form. But today we are not focusing on it. But in general, you would obviously need a rock which has lots of pores in it, so that it can absorb of all these gas and oil and keep it within them. So something which has got a lot of porosity. So that is what you would define to be the main reservoir. Once you have defined a reservoir, and you know that you have a seal above, so that is again very important here. So something where, it's a kind seal would be a kind of rock which will not allow the oil or the gas to go past. No, it will not allow it to come into it, and will not allow it to flow through it. So if we have a seal sitting above a reservoir and we have a source somewhere wherein this oil or the gas can migrate into the structure, then we know that we have most of the things. We have already answered, the few basic things that are required for a petroleum system to be available there. So just to reiterate, what were the questions we were answering? We were seeing whether there's a boundary. Where is the boundary of the basin or the block? How far is your area where you have got the oil or gas? Is this area suitable for hydrocarbon generation? Do we have a source somewhere wherein the hydrocarbon can come in? Is there any possibility of the hydrocarbon entrapment? Do we have the specific structure required for the hydrocarbon to be entrapped? Do we have the proper seal rocks sitting above or beside, wherever it's trying to seal it, entrap it? And what is the last question there is on any manifestation of hydrocarbon available on the surface, because that is something which will give you a clue. And so when we are talking about surface, we will talk about a little later just about things that you can see on the on the surface, on the seismic data. You can see on a seabed. What are the things that you can see on seabed that can help you think back and see if you have a reservoir there? So this is primarily as an interpreter in oil and gas, with what we would be looking at to answer our questions about a petroleum system being available there or not. So now when, I've been talking quite a lot about seismic data. What do we mean when we say a seismic data? So of course, that is a data which is acquired. It's a very expensive data because it takes a lot of effort and money to acquire them, and it can be acquired both onshore and offshore. So the first picture here gives an acquisition onshore, and this picture here is a cartoon of an acquisition offshore, means on the water. The methods are pretty much similar, though the instruments used are slightly different from each other, depending on what would work on land and what would work on sea. The basic principle is we send some acoustic signals. And what do you mean by acoustic? In very, very limited language, if I use, say if you really thump out with say if you stamp your foot on the floor, you make a noise, you generate some energy, which is transmitted. So if somebody is doing that on the first floor, sitting on the ground floor, you would hear that. So obviously that is some energy that has been transmitted. And that is a very basic principle that we use in acoustic signals. We make some kind of thumping, a noise, which is then propagated. It's sent across underneath, and then we measure. So we measure how much of sound we send, what time we have sent it, when we have received it, and we try and assume from that what's the, how far is where the reflector is. We'll come to that a little later. But just in terms of the picture here, this is an onshore, and what we see here is a vibro-sized truck, which I'll show you a little later, also better pictures of those. So that sends out some signals, which then gets reflected back from a surface and into another receiving truck where you're measuring it. And offshore, what's happening is you have got a tail of hydrophones laid across, and it's where you receive a similar kind of signal. And if I show you a little better pictures, this is me, this is a shallow seismic boat, and which does pretty much similar thing as an offshore, which is, this is a bigger boat, which is doing a bigger survey. These are on land, and believe me, I am that shallow shadow sitting there in that vibro-sized truck. But what this truck does is, if you see this base plate here, so it has got something, just kind of a thumping pad, and it really thumps really hard onto the ground, and it sends out the acoustic signals, which are then received back and measured. And on the offshore, I'll show you a little more as to how that is done. So this is a picture I had taken from that boat where I was standing outside. These are the interiors of that seismic vessel, the back deck, as we call it. We have air guns. Now these are just very basic pictures. Obviously, when you're talking about air guns, you get much more, higher energy stuff as well. But the basic principle being, again, that this is, it sends out an acoustic signal using these air guns, which are then recorded using what we call, this is the streamer section, and you've got all the data coming in through the cables. This is just a workboat, which is normally there at the back deck, because if you need to lower down into the water. And of course, the streamer deck, which is used to lay your receiving and your, the tools for sending out the signals. So this is, in short, this of course is a lot more required to acquire a data than just what we are focusing here. But these are the very basic principles that's used in it. And then comes to the next stage is a seismic processing, which is a very, very specialized, and it needs a lot of higher mathematics included. So we will not go into too much of detail, but very, very lightly, if we talk about, as we said, say, if you look at this diagram, you've said this is a source array. So that is somewhere we are sending the signal, the source. And of course, you've got these receiver groups wherein we receive the signals. And if you look at each of those, say this, if this is a particular reflector where it is getting reflected back, each of these signals get reflected back and is coming into a particular receiver. So these are each kind of a data set for each of these. We measure the time it has taken to come in, and the signal comes in. So as an example, if you think that this is a kind of structure that we have underneath the surface, which is what you're trying to map, and if you think about each of these receiver signals that you have received as coming, the first one comes from this point, the second one coming from this point, and you are getting these individual signals which are then stacked together. And I'm trying to make it sound very simple. A, because we won't be able to cover all of that in today's presentation, and B, because it is not my specialization. So there is a lot more that is involved in it, a lot more processing. You need to cancel noises, and there's a lot of mathematics and algorithms that are used to actually generate these seismic data. But again, as I said, in layman's language, you are basically trying to image what is underneath the surface using these acoustic signals. So once you have that, you get what we call is what we normally have on our workstation as a seismic data. This is again just it's a random line. It's actually from Angola, if I remember, deepwater Angola. And what we see is, again, as an interpreter, when you see a seismic section, of course, what you have, this blue line here drawn is your seabed, which have mapped. Then the red one here is again a very important marker, because we can see there's a distinct difference in the amplitudes of the sections there. So obviously that's a very important unconformity which has been mapped. What you see here down here is very chaotic, because that's a lot of salt structures, which we will talk about a little later. And what we see above is much less chaotic and more order and in conformance things. So these are all kinds of interpretation. The moment a geophysicist sees on the workstation, he or she gets a seismic section, and they try to delineate these different reflectors which could be important. They try to look at the attributes which could be important. Say if you're looking at a reservoir and you're looking some very bright amplitudes, it could be because you've got oil and gas there, so you're trying to look at that. You try to map it all over around a 3D data set to map the structures, to see what kind of structures if you have, can you have any reservoir there? And so these are all the whole petroleum system that I was talking about. We try and assess based on what we see from our seismic section. I think I could have gone into much more detail about interpretation, looking at the reservoir section. But I just thought, because though for the first 18 years, that is what I've primarily looked into, the last 2 years, I worked in great detail on looking at everything above the reservoir. And I thought there could be some fascinating things that I have seen, which I wanted to share with you all today. And this is another specific stage in the oil and gas industry even, or other industries, where you have the geophysical site surveys, which is not only, as I said, not only limited for oil and gas exploration, but in other stages of the oil exploration as well. So if you want to, for any reason, if you want to do a pipeline survey, if you want to lay any cable, or even if you're doing abandonment or inspection surveys, you would need these geophysical site surveys to be done. And of course, nowadays, wind farming, wind energy is, it's one of a very important renewable energy that the whole world is looking at. And in order to set up these wind farms as well, you need what is called a geophysical site survey. But of course, when I will talk to you about site surveys, mine is mainly focused on, again, exploration in oil and gas industry rather than wind farm. It's just, I haven't had the opportunity to work in any, but I just thought I'll mention them because there's a lot of geophysical work that goes on into these industries or setting up these projects as well. And why do we need, especially in the oil and gas industry, why do we need these kind of site surveys to be done? Of course, because we don't want anything of these to have happened. And it has happened, not once, but multiple times. And we have had a lot of loss in property and human loss. And it's something which nobody would want to have. So every time you want to drill a well, every time you want to do any survey, you want to lay any pipeline, we would always need to do a site survey as such. Now, what does this, when we call about a site survey or looking at geohazards as such, what does it include? What are the things that you would look at interpreting when you're looking at geohazards? The first thing is fascinating. These are pictures from West of Africa, both including this one is from Senegal, offshore Senegal, and these two are from offshore Angola. And what we see here is what we call the seabed or the bathymetry here, and it's very, very varied. I mean, we can see things like, it almost looks like, if you look at the picture, it would look like a river flowing into. Well, these are almost huge, deep canyons that is seen on the seabed. And when we're talking about seabed, this is ultra deep water. This is about, 2.5 to 3 kilometers where you actually see of water depth. So the first time you see seabed is about, you can imagine 3 kilometers, the water is sitting above it. And so it is very, very important, even for a drilling rig to come in, if they have enough, where would they be setting in their anchors, and what is it that they're going to find on the seabed? What do we have? Are there any deep canyons where possibly they could be sliding, there could be risk of anything, you know, being very loose and very coarse. So we have to look into those. So that's why the first thing we do in a geohazard survey is map a seabed and map that in really great detail. And the red spots here that you see are kind of pockmarks, and we'll talk about it a little later. We've got these kind of big ridges at the sides and a huge, of course, that's the slope. So that's kind of almost a break. You've got a shelf break coming in from on your seabed. So we were talking about the first thing that we see is these huge canyons, or we call them Paleo Canyons. Paleo because these are the Paleo Canyons, which were huge canyons before, but then they got filled up. So you've got the Paleo stage, and then you've got present day canyons sitting on the seabed, which is of course very, very, they are very steep, and they could, you know, sometimes you cannot really drill through any of those if it's more than about 5 to 6 degrees, but these are sometimes much more, they're much steeper than that. Then you can see some, this was fascinating for me, so I've kept this picture. This is, these are coral mounds. And I know we've got friends from Australia, and if you're thinking about corals that you can see offshore Australia, they're very similar, but the only difference being is these are not live corals anymore. These are cold corals. So they were corals, you know, live corals, obviously in Paleo age, but over the time, those coral reefs have died. But what we still have left behind are the coral mounds. So these are kind of remnants, and you can see it on the seabed. The corals always live forming these mounds. And if you look in a 3D map view, you can see these mounds. These are remnants of the earlier corals that were there. And you can see they always form colonies together. So you can see these 3 different colonies of corals, you know, obviously much, much earlier in the Paleo age, they all lived. Then I was talking about these pockmarks, or, you know, kind of giant pockmark fields. And what are these pockmarks is basically what happens deep down if you have a lot of structural movement, and you have these kind of salt structures. Salt structures are more like, you know, as I said, I can explain them as a jelly, or they're very, very wobbly and they move around. And because they're moving so much around, they create huge structural, you know, deformities, if I say, above them. And due to all these stresses, sometimes what happens is, because you get all these faults coming up from the top of these structures or the side of these salt structures, and along these faults, what happens is you get very, very a large number of gas seeps that's coming off along the faults, because there's a place, there's almost an opening for these gas to come up. And what they do is, once they reach the surface, they kind of pop out. So if you think about a bubble that bursts out on the surface, these are all these red marks that you can see on the seabed here. These are such pockmarks, which have been caused by either gas seeps or some kind of stress that is generated inside. Is when it is bubbled out, it almost creates a small, very, very small volcanoes all around, and creates these kind of pockmarks on the seabed. So, and then you've got what we call in a deep water geology, they're called mass transport deposits. So these are, if you think about, say if you have a big mountain, but all that's crushed and it's just flowing down, crumbling down like a landslide, a huge mountain falling across with loads of debris along it. These would be, you know, you can imagine them to be these mass transport deposits. And if you see on a seismic, it's this particular section or this particular section here. So it's kind of all kind of debris, which is all rolled and mashed and crushed together, and they all flow along big transport deposits. And these are again a big geohazards when you're drilling or when you're trying to drill through them, because they're very loose and you don't know what's there, what's the kind of pressure they can have within them. So there are loads of things that you have to think about when you see these kind of mass transports. So you always have to be very careful in interpreting them. And of course, I was talking about the salts, and these are all different. These are sections that I've come across in my work, and I have just collated them onto one slide. And as I said, it's almost a very mobile, a jelly, wobbly kind of creature which can flow in and out from anywhere, and they form different structures, which gives rise to other forms sitting above it. So first of all, because you can have these kind of upward culminations, what they can do is you can have big anticlines sitting above or in the salt structures. They can give rise to these kind of faults, along which again you can have a lot of oil and gas sitting across them. But of course, whenever you see a salt, it gets very difficult to image anything because it's very chaotic inside, and because of the varied structures that it can give rise to, it almost gets very difficult to interpret anything if you have such big salt structures sitting below it. But there is a lot of oil and gas exploration in a lot of other places where you have got these huge kind of salt structures, and it's a very important bit that you need to look into when you're looking at bigger picture of the oil and gas as such, in terms of its exploration, or even for the geohazard survey when you're looking at if it's safe to drill in there. So in geohazard mapping, you would combine all of them together and give wherein you can advise as to what would be a better place to drill, where is it safe to drill, where can a drilling rig safely come in, anchor, and or if it's a jackup rig, you can suggest people based on your interpretation of the geohazards. So of course I could have talked a little more into kind of the reservoir interpretation bit as well, but in terms of time, I think I have spoken a lot, and I will just finish with a very cautionary tale, and then we can open up for questions. This one, again, I have to give thanks to Abhishek, my husband, who had shown these slides to me about maybe 10-15 years ago. But every time I give a presentation like this, I always try and finish it with this because I love this. And what this shows is you have, what do you see in this picture? Anybody wants to unmute and talk? I'm happy. What can you see in this picture?
Clouds.
Clouds, very good. Anything else?
Some houses.
Some houses, okay. But primarily in the bigger picture, you see a lot of clouds there, right? Okay. But as a geophysicist, I would say I can possibly see a little more than clouds. What can you see now?
Rats.
Yes, you can see some rabbits, maybe. Yeah, an elephant, maybe a big giant teddy bear,
Crabs.
and robot machines. So a geophysicist in general, I'm not saying this is what we do. We don't actually paint pictures on clouds, but this is just to say that we are still interpreters. So when we see a seismic, there is obviously a lot of bias which is involved in what we interpret and what we see. So it is quite, it may differ from one person to another as to what they are seeing on a seismic and how they interpret. And the cautionary tale here is just to add that there is always an interpreter bias in everything that as a geophysicist.
What do you need?
We suggest or we say. But I'll finish with one last slide, which just shows if you can actually work on the data set, the seismic data set, and there are ways to improve it. So when the bit that we didn't talk about much is the processing bit, and it is also a very, very important part of the whole seismic data set, because somebody who works in the processing can give you a much clearer picture, and therein a geophysicist and as an interpreter, if you're looking at it, you get a much better picture, a clearer image of what you can see. So if you have a much clearer picture, and you don't have to think much, and you can say, yes, definitely I can see some rabbits, I can see an elephant, I can see a teddy bear. So those would be your final results. And again, of course, the three main bits that we have spoken about is an acquisition, a processing, and of course the interpretation, and an interpretation in various kind of sections, both in the reservoir section and everything above. And I think with that, I will finish my talk here and open for any questions that anybody has. I'll try my best to answer them.
Yeah, thank you so much, Ipsita. Thank you. That was a very wonderful and insightful presentation. Thank you so much. I've learned a lot.
Will we do a quiz?
Yes, just hold on a minute. If you have any questions, please pop them into the chat box, and we'll get Ipsita to answer the questions for us. So I have one question here. The first question here is, what is migration? And that's from Ibn. Okay.
When we're talking about migration, what I meant there was, say, the oil or the gas, the hydrocarbon has been generated far away somewhere in the kitchen, and you have a structure sitting there. So the oil has to migrate, it has to have a pathway. So it has to have specific kind of rocks wherein this oil can flow into the structures. And that is what you mean by a migration. So wherein this particular oil has a definite pathway where it can follow and come into the structure. And it happens over the time, over millions of years it happens, but that has to be present, that a particular structure, that particular kind of rocks has to be present for it to happen. So that is what we call, as a migration here.
All right, fantastic.
Thank you.
Yeah, so there's another question here, and it says, how is strike direction important while taking onshore measurements? So it says, how is strike direction important while taking onshore measurements? Is it always necessary to set profiles perpendicular to strike direction?
I would say, again, I'm not a complete, acquisition experience much. So I would, but as much, to answer your question, I would say that yes, it is important, but I have seen surveys which are not always in perpendicular direction, not always in the strike direction. I've seen a lot of surveys done, depending on other factors like, just it could be logistic reason, it could be like especially offshore in terms of mainly logistics, but onshore as well. I have seen other directions as well, but that is what you would prefer.
All right, thank you. So there's another section, another question here. I'll just ask that now. It says, how can we identify clay from groundwater zones using the seismic method?
How can we identify, sorry, couldn't hear you.
Groundwater, yeah, from clay using the seismic method?
Good question. We did study a lot of groundwater. Can somebody else answer the question? I'm quite happy to let somebody else answer it. I wouldn't exactly be able to tell you, but these are.
I can have a go.
Yes, Abhishek, please do.
For groundwater exploration, we generally use a different method called resistivity method, mainly for groundwater. But with seismic, it is not difficult. What you're trying to do with seismic is you are trying to measure whether the rock is filled with oil and gas or whether it is filled with what you call brine or groundwater. So if it is not filled with hydrocarbon and if it is a reservoir rock like sandstone, it will most likely the pore spaces will be covered with water. So it is almost a very indirect way of saying that if I don't find hydrocarbon or oil and gas, I will find water. But that's not a direct method for exploring.
Groundwater exploration, that's right.
All right.
Thank you.
Thank you so much. And just one last question. So that question says, what subjects do I have to study in secondary school or high school in order to become a geophysicist? Yes. And what grades should I get as well?
Absolutely. I think you will have to have maths and physics for your secondary grade. Those would be the two most important subjects that you would have to keep. And of course, past that, you can do, I think in UK, you do have, as an undergrad, you have geophysics as a subject, and you can take it up. I know in India, when we had to do a physics graduation before we could do a specialization, a master's in applied geophysics. But in UK, you can still do an undergraduate degree in geophysics. But main subjects, to answer your question, would be maths and physics is what you need.
Wow, that's fantastic. Thank you so much, Ipsita. That was a wonderful presentation.
Thank you so much.
To having you again very soon to come and give another presentation in the future. Hope you
Sure. I would love to do that. It's my honor being here. Fantastic.
We're so grateful for that. And we'd just like to say a big thank you to everyone who has joined us today. We have another presentation coming up in 2 weeks' time on the 31st of October. And we're going to be talking about engineering, wind engineering. So is it CFD of wind engineering? So that's what we're working on next 2 weeks. So make sure you join, you go to Eventbrite and register so you can get your Zoom details for that event. So we look forward to seeing you in 2 weeks' time. Yeah, that's about it from us. And so thank you so much for joining us and have a lovely weekend. So see you in 2 weeks' time.